Hi again. So Christian couldn't make it, so I'm replacing him on the spot.
So hopefully he'll make it next year.
Yes, hopefully he can make it next year. So connection tracking for mobile use cases. So I'm going to deliver you the introduction, and Anita will deep dive into the details and the numbers.
So I will take over Christian's part, and he's taking over mine.
So from a very high level perspective, so this is a telco network. So this is processing calls, and this is a lot of elements that we call a VNF. So typically you take a one ATCH chassis, so one box. This is one VNF composed of multiple blades. And with virtualization, the first, where we are now, it's basically you have one blade equal one VM, and you take all of these VM, that's one VNF. At some point, this is going to be chopped into microservices and with container, but this is what we have today. And this is this kind of, whoops, sorry. So within this infrastructure, so we are looking at the EPC mobile traffic profile. So the EPC is the part of the network which is right behind the antenna, so between the antennas and internet, to make it simple. So you see all of the traffic of the user coming. So the majority of the traffic are short duration flows, but you have a lot of them in parallel, like millions of flow. You have a high incoming call rate, so you have between 100 to 200 connections per second per user, I believe, because we have way more. And this put pressure when you deploy a vSwitch with contract enable to track all of these connections. So that's the challenge with the mobile, because here we have a lot of churn into your contract table. Also, there is a wish to reuse the contract statistic for billing purpose. So it has to be accurate. You don't want to lose any contract. Now, if you want to simulate with a traffic generator, this kind of, if you want to inject into one of these big VM with OVS-DPDK under it, you will use a traffic generator to create this kind of traffic. So this are already presented as this morning, so same numbers. So, but here, this is a view from a traffic generator perspective. So we have, for 10 gig of mobile traffic, 200K flow created per second. So you start on the left with 0 flow created, and you start at 200K flow per second. After 5 seconds, you hit 1 million. The first flow expired, and you create and you destroy as many flows as you create and you destroy as many flows. So your number of flow is steady. And at some point, you stop to create flows, and you tear down the number of flow. So this is, if you use a traffic generator, the kind of traffic profile that you will have. And while you're in the 10 gig state, at 10 gigabit, so you will have 10 gigabit of traffic, 4 millions of packets per second, average packet size 600 bytes, but you will have a lot of small packets. And on top of that, here it's 1 million flow, 1 million contract. Because that's a bidirectional 5-tuple. So now, we talk about this very complex traffic profile, and most of the time we come up with numbers with packets of 64, 1500 bytes. So why? Because typically, the packet size does not matter because we just access the header. You just access the header of the packet to know what to do with your packet, so you don't care if it's a small packet or jumbo. Except with our PVP case. We have a big fat VM that will get out of the packet, so you have a vhost user copy. So we need to check for the small packet and the large packet if there is an impact of the mem copy. So that's why so the packet size will affect NFV performance. Also, in terms of flow and connection, so if you think about a flow table, so flow creation and flow destruction will have an impact on your performance. So when you create a flow, if the flow is not in the table and not in the cache, you will have an opcall, and at the flow, you will have to allocate things in your contract table. When you destroy the flow, you have to flush you have to have a strategy to reclaim, to recycle your bucket entries. So, and you're doing that while the packets are flowing in. So you don't want to have locks and this kind of thing. So while you create and destroy flow, and you have packet getting through full speed in a run-to-completion loop, you may have problem and drop in performance. Also, the performance may decrease if your table is full, because you will have some collision in the table, and also because of the rate of incoming flow, obviously. And what metrics do we want to measure? So we want to measure for various packet size, how many cycles per packet we spent with the latency and the jitter. And we want to know that for various core number to see if the performance scale. So I want to know if my performance with 10 core is 10 times the performance of 1 core. I want to check if this performance is scaling with the number of contracts. I've got 100 contracts, I've got 1 million contracts. Do I have the same performance? Same with the number of IP routes. And always, we want to check all of this. So this is a gigantic matrix that we want to get, a lot of numbers. And finally, the units to measure the performance. Usually, so we use RFC 2544 for individual tests. RFC 2544 loads your system at 100%. It means that you spend 100% of your cycles to process packets. It means that you cannot process more. You're exactly loaded at 100%. So for a given clock speed, you can calculate the number of cycles per packet. This is why we use RFC 2544. And from this number of cycles per packet, you can derive the millions of packets and the gigabit, and you have the formula here. All to say that all of these numbers have to be collected by an automated framework, a test framework. So we use vSperf at Red Hat. And we already presented this slide this morning, so I'll be brief. The main thing to remember in our protocol today, and all vSperf tests and all the code is upstream in vSperf project, we use RFC 2544 with 0.0 packet loss for 2 minutes. It's not 2 days, it's 2 minutes. You don't drop any packet for 2 minutes. We use UDP flows, 5-tuple change, so we refer that as flow. And we use test PMD in the VM, and we use T-Rex or a Xena traffic generator, but we don't use iPerf. You cannot do NAV performance measurement with iPerf because iPerf is your bottleneck. So you need a telco-grade traffic generator.
All right, I'm going to cover the contract test results. And here is our team, our QE team, especially Christian and Kishan, who have worked on a lot of these results, and the dev team for reviewing it, Aaron and Flavio. Aaron's here, Flavio didn't make it. This is an expanded of the test profile. This is for testing stateful TCP contract. In this use case, it's pretty much what Aaron explained earlier. We're running a very simple TCP flow. We have the SYN, the SYNAC, and data, and then the FIN and the FINAC. And so you have a client and server port, and the client initiates, and the server is replicating, getting the termination. And OVS over there is just receiving these packets and shipping it out the other NIC, other port, because the VM is just doing a MAC swap, not doing much out there. We're using a T-Rex packet replay and IPv4 packets, 600 bytes. Short calls, 5-second timeouts. And the timeout is in play for cases where the FIN or the FINAC don't make it, and the call is terminated after 5 seconds. And the goal is to scale up the number of connections. We will do both. First is to benchmark with static number of connections and what the throughput is. And then the next step would be, what is the connection rate that it can handle? This is a very simple contract flow, and it's like a mega flow coming down. You have a source and destination variation and on the IP address, and the port is kind of static. It could be UDP or TCP, and we run both those combinations. We are running OVS 2.7, DPDK 16.11, so we may not have all the new contract fixes and enhancements. But we will hopefully get that in the next release. So this is looking at, the color. The last one is supposed to be green, so I'm not sure why it showed it as black on that. But the goal was to match the colors up. So let's look at, this is a throughput test, and we are going to expand the number of flows. We start off with 1K in blue, and then we are also looking at EMC, enabling and disabling EMC, and this is OVS contract. So this is kernel mode contract, not user space as yet. And over here you can see the blue line shows baseline, no contract. What's our performance like? For 64-byte frames, we can do around 400K plus packets per second. And then you see that as you add a first tuple, as you add just an IP source, and then you have IP source and destination matching, and then you have a 4-tuple, which is IP source, destination, and port matching, and then you have 5-tuple, where you could have a port protocol or something matching on top of that, or a VLAN. So you can see that your performance for contract varies slightly, goes down a little bit, whereas you add more tuples, but then 4-tuple, 5-tuple seems to be pretty good too. And then you move on to EMC disabled. You can see that when you have 1K flows, you actually take a performance hit on your baseline, disabling EMC, but you get better performance on your contract, slightly better performance on your contract. Then moving to 100K flows, which is the orange indicator there, that is with EMC enabled. That's showing we take a 50% hit in the baseline itself on just enabling 100K flows. And then when you enable contract, you can see there is a slight hit as you enable contract just with that. And then with EMC disabled, you do see a performance bump in this case for 100K flows. And you see it even for the contract use cases. And this is OVS-DPDK. This is, again, a throughput test. Here we don't have the EMC because we'll look at that next. Over here we have 1K, 10K, and 100K flows. And you can see from 1K to 10K, there is not a significant change, even in the baseline, and even when we just ran the 4-tuple for this, there's not a significant difference between 1K to 10K flows. But contract does have an impact, almost a 50% impact, by turning on contract here. This has no VXLAN enabled. This is just flat or VLAN traffic. And then when you have 100K flows, your baseline is already lower, and then you are now turning on contract, and you have another 50% hit on contract when you turn it on. And this is just showing EMC enabled or disabled with OVS-DPDK. There is a performance gain with 100K flows, but not a lot. Because if you're talking millions of packets, it's like under 5% improvement. Now looking at our next step where we want to test connections, the connection rate, how many connections per second can we handle? And this is, again, OVS kernel going to traditional Open vSwitch, where we have all the tunables that Aaron talked about. We can actually track the number of open connections, the stats. We can actually set a bunch of timeouts here. And we've set them all to 5 seconds. And we can now vary like what Franck pointed out earlier, we're trying to build this graph. We're trying to plot this graph and start off with, say, an example here, 10K connections per second. So by 5 seconds, we should have 50K connections. And at that point, we start dropping connections. So we would have incoming 10K and dropping 10K. And we run for 300 seconds, 5 minutes. And then we ramp down. And that's our goal for the test. And for user space, we have some limitations because we all don't have all those tunables available, so we cannot set the connection timeout. There is a default timeout already in there. It's around 30 seconds. And we're seeing that our connections are taking around 32, sometimes 35 seconds to time out. They're not timing out just based on the fin and the finac. They're waiting the whole time. You cannot query the table entries right now, or the stats. You can dump the whole table. That's available. But you need to do it pretty quick, like every second for these tests, and we're not able to do it right now. So there's work in progress. On the user space contract definitely has work in progress. The table size is restricted to 3 million entries. So given that restriction, if we run 50K connections per second, we have 1.5 million connections active. And if you run 100K, we hit the table max. We would like to reach 200K and 6 million connections. That would be way beyond the table size right now. We can't change it. And ideally, we want to run only 5-second short calls, and we're not able to do that either. So let's look at the results. The OVS kernel results are the blue line, and you can see that some of the user space, we don't have a lot of data right now. We're still working on it, and the results are not all that great. There is more work to be done on the user space contract. On the kernel side, it is, I think, within expectation of what we're seeing. So we have data for TCP, where we have no data, and we're just having the SYN, SYNAC, and terminating FIN, FINAC. And then we have with data 600 byte packets and 800 byte packets. And then you have UDP here with 800 byte packet data. And you can see that UDP has really good performance right now. It's like almost 100K connections per second. That means you're reaching 500K steady state entries. TCP without data looks good. And both with the HTTP ones are about between 10K to 20K, which is expected. Though we would like to see definitely improvements there. OVS-DPDK, with the data, we are definitely affected by the timeout. So this is a 30-second timeout versus the other one was a 5-second timeout. So we're seeing 55K, and I think our UDP data could go higher, but we're hitting, I think, table limitations on this one. Moving to our final conclusion and saying that this is our benchmarking plan that we're looking at using OPNFV's VSPerf. We are somewhere around the second block, and what we're trying to do is, the first goal was just SRIOV and base OVS and OVS-DPDK testing, and test BMD as a vSwitch. So we've done 64-byte, 9K jumbo frames, and measured throughput latency, single NUMA, and very basic multi-queue. And then just on the overlay tunneling, VLAN flat and VXLAN bonding. And now we're moving to more realistic profiles, trying to make OVS-DPDK ready for NFV performance with mobile traffic flows and scaling contract multi-queue, and we're looking for better RxQ management, live migration across NUMA. And then we would like to get to the right, where we're moving to more vRouter and firewall type features with connection tracking, where we're tracking the connection rate, and having more overlays for service function chaining, and moving to hardware offload, OVS hardware offload, BFD, CMP, and L3, L2 EVPN. Thank you.
All right, let's thank our speakers. We have time for questions, so if you have a question, come up to one of these microphones, or raise your hand and I'll hunt you down. Okay, so I have a question. So your numbers there toward the end showed that OVS-DPDK was getting much higher connections per second for some of the cases than the kernel implementation. I would have guessed that since the user space implementation was relatively mature, it's newly implemented, and it doesn't use some of the more advanced locking technologies like RCU and so on. I would have guessed that the initial implementation would be on par or slower than the Linux kernel implementation. Do you have an intuition why it's faster?
So we're actually expecting it to be better, actually, than the kernel. But yes, the locking mechanism is not there, and the timeout issues are not there as yet. And we have to debug more of why we were expecting at least maybe 10 times better.
Okay, well, what's the intuition why it should be 10 times better, I guess?
Because it's running, I guess, not running through kernel contract. You don't have interrupts. You're running full speed down. You're running. So with DPDK, you should have that benefit of the connections.
Okay. Okay.
I would have said that because we're not full feature yet in the contract user land, with less feature, I would expect to be higher. And maybe once you have all of the feature, the performance will drop as well. So the locking mechanism, LRU versus a spin lock, if the spin lock is fast, and we didn't have a lot of core in line, I think there was no contention. So basically, I think because we have less feature, enabled, that's why it's higher performance.
Okay.
I believe.
Any questions? Yeah, we have one over here.
Thanks, guys, for that. That's a really great, a lot of work there and a great amount of information to see for real use cases. Like to see that. I just wanted to ask, I'm sure it's somewhere in the slides, I probably missed it. Was this traffic actually going to a virtual EPC? Was it actually going through vHost user?
The traffic is going through vHost user.
It is actually going.
It does.
Okay.
It does reach the VM, and the VM does a test PMD is running. It does a max swap and pushes the packet out back.
Okay. Great.
So it's going through vHost user.
Yeah, that's great. I look forward to seeing the slides when they're published and stuff. So thanks.
Anybody else?
Thanks for the nice slides and that nice presentation. In one of the slides, you have mentioned that the results are different with EMC enabled and disabled. So what could be the reason? Is it because of the EMC size?
So with OVS kernel, we are seeing EMC have a improvement. But it's not that, I think the improvement is there in both cases. It's just not as visible with OVS-DPDK because it's around 200K packets per second performance improvement. But it's not as visible with OVS-DPDK because we're talking millions of packets per second at that point, and 200K doesn't make a big difference at that point. But with OVS kernel, it's like 25 to 30% improvement, and you see it. It's obvious.
I was referring to the OVS-DPDK.
So OVS-DPDK does have a performance improvement when you're running high number of flows, like 100K flows. Then you're seeing between 100 to 200K packets per second improvement. You are seeing an improvement, but it's not significant. You can see it's like a small bump in the graph.
Anyone else? All right, let's thank our speakers again.